we were talking about discrete random variables. The variables that kind of the values that it could take on are islands, or you cannot take any whatever value you want. And we learned how to do PDFs. So if you think about the PDF of a random, discrete random variable, you had the variables, the values that it could assume, and they were discrete, right? Like they were, you could list them, okay? If you can list them, it's a discrete random variable. Now we're going to talk about a continuous random variable, okay? So just to recap, what's a continuous random variable? For example, heights. Heights, if you choose people at random, heights are random, are a continuous random variable. If you think about the heights in centimeters, I am 164.3, right? The 0.3 is just because I want to be taller, but it's 164 centimeters, right? You could be 164.21, 23, depending on how accurate is your measure, you can take whatever value you want, okay? And you can have weight, height, length, temperature, pressure, speed, all of these kinds of natural measures, they tend to be continuous, okay? So between, for example, between 160, if you say, oh, I measure 164, 0, it might be that it's not that. It might be that you measure this, and your scale is only able to get this digit, okay? You'll never know, like, how many electrons and protons I'm made of, and measure the mass of that, like, that things, okay? So we're never so precise. Okay. So, as a result of this, as a result of having a continuous random variable, there is never a probability that you're exactly a number. Okay? So what's the probability of Louisa being 164.0 centimeters? Well, it's 0. Why? Because when I say 164.0, I'm saying that it's 0, 0, 0, 0, 0, 0, 0 forever after the point, the decimal point. Exactly 164, I'm not even sure, right? My measuring tape can give me that. But I might be 1.64.0000001, okay? So there is you'll never be an exact number, okay? Yeah.
So, like, what's like a definition that we could use for continuous, so we can like separate it from discrete? So, like discrete, you can list everything out. How, like, what would you say for continuous?
You cannot list.
So you just can't list that?
No, you can't list it, okay? So. And the probability of being exactly some number is 0, because actually you never know how if you think about this is forever zeros after the decimal point. And we never have a precision, because you might be this, for example, right? So it's a very interesting consequence is this. When you're talking about the probability of having something small, your variable being smaller than a number or equal to, is actually that you can drop the equal, because the probability of equal is 0, right? So the probability of Louisa being less than or equal to 164 will be actually the probability of Louisa being just less than 164, okay? Because equal, I'll never be equal 164, okay? So this is a very important consequence of having continuous random variables. So with continuous random variables, we can only work with a range of values. You will only work with less than or equal or between 2 and 7, right? So it is much easier to ask this question: what's the probability of Louisa being bigger than 163.9 and smaller than 164.1? So this is kind of, Louisa is very close to 164, but I can never say that she is 164. I never will have that precision. So usually, when you want to find the probability of a particular number, you take a small range around that number, okay? So with continuous variable, you will never see the probability of x, of y, whatever random variable you're talking about, being equal to a number. It's only smaller than or equal, bigger than or equal, or in a range or an interval, okay? So let me show you this. I just got this out. So let me show you this. In the end of the day, the probability of x being less than or equal to, I don't know, 2, will be the probability of x being less than 2, because the equal doesn't matter. It doesn't matter. I don't care. This won't change, okay? Because the probability of having a particular exact number is always 0. The probability of having x greater or equal to 2 is the probability of having x greater than 2. The probability of having x in between 2 and 3, 2 and 3, will be the same thing as having without the equal signs. All right? I'm dropping the equal signs. Right? Cool? All right. Questions about this? So, here is the definition of a PDF for discontinuous random variables. We saw that we have PDFs for discrete random variables, which is a table where you have the variables that the values the variable can assume in one column and the probabilities in the other column. But now we cannot list them, right? We have a problem. Houston, we have a problem. We cannot list our variables. So what we have to do is think about this. Imagine the PDF of a discrete random variable being a histogram, okay? We saw that we can actually transform the table into a graph, okay? Now think about this discrete random variable that could assume only these points. Think about it now having, it's being able to assume more points. It's getting closer together. The points, or the bins of the histogram are getting narrow. Okay? The bins of the histogram are getting narrower, I don't know how to say that. And keep going. What is going to happen? In the end of the day, if you take what we call a limit, for those who will take calculus, in the limit, like if you keep narrowing, if you keep letting your discrete random variable assumes lots of values, right? In the end of the day, you will have only kind of lines that are close together, okay? You'll have lines that are close together, and in the limit, if you make this discrete random variable able to assume any value, you will have a curve, a continuous curve, and not a bin anymore, okay? So in the end of the day, the PDF of a continuous random variable is a smooth curve. It's a smooth curve, okay? So here's the definition. For a continuous random variable x, capital X, now the PDF will change its name. It's not probability distribution function. It's actually called the probability density function. It changed a little bit the name, okay? And it's a function that, if you graph it, if your random variables starts in A, ends in B, you will have a graph. You will have a curve that has an equation f of x. Okay? This is the definition of the PDF. Now we're only graphic because we can't list. So for a probability density function, we don't have a table anymore. It's only a graph. It's only a graph. It's a function. This whatever this curve is, it could be a line, it could be I don't know, something more squiggly. Okay? You will always have a smooth curve as a histogram, okay, of that function. And you have a formula to describe this curve. We will see that, okay? Cool? Up until now, is everything clear? All right. So, here we go. So, you have the PDF is actually a histogram that your variable now can assume any value, so the bins are so narrow that you connect the dots and this transforms itself into a line or a curve. Okay? For example, this graph here is a random variable that can assume A up until B, any value between this interval I can accept. Okay? And f of x will give me the probability. Okay? Not directly. We will see that it will give you a probability, but you will have to do an operation before getting the probability. This graph here is also a variable x, a random variable x that can value A to B, but it can value anything in between. I cannot list it. And I have another function here, fx. In this case, it's a line, right? This is the histogram. If you would imagine a discrete random variable, you would have the bins like this, okay? But you are making this bin so narrow that like you're connecting the points into a smooth curve, okay? So if you want to get the probability from this PDF, right? Because PDFs give me the probability. In discrete, I have the values, and here I list the probabilities. In continuous, how can I get the probabilities? If now I only have a graph, I don't have a table. Well, it's the area under the curve. Okay, so what's the probability of my variable x be between A and B? Okay, it's the area. So if I shade this is the area that under the curve. Okay? Do you remember that for bins, when we were talking about discrete histograms, the probability was the area of the bin? It's the same concept, but now we have the area under the curve to give us the probability. Okay? And we're going to do some exercises to understand that better. One characteristic of this function is that we have no negative values, because can probabilities be negative? No. So if you see a graph that the function passes to the negative values, this is not a PDF, right? It's disguised and it's just cheating. It's not a PDF, okay? So we don't have negative numbers on the PDF. Okay, so let's do an exercise. Let us do an exercise. Let me just drag this here. Let me copy this. This was from the other section. Let me copy this here to a new slide. Okay. So here we have. Suppose X is a continuous random variable. Okay? With density function f of x, whatever formula it is. Okay? If x can assume values between 1 and 5, I cannot list them, but I know they are between 1 and 5, and f of x is 0 otherwise, find the probability of, let me see the question again, of x being less than 4. So, all right, let's break this down. This is the question. So suppose x is a continuous random variable, okay? So I know that the PDF is not a table, it's a graph, okay? It's a curve. And x can be between 1 and 5. Look at this information here. X can assume 1 and can assume 5, okay? Now, the curve of the PDF is given by this equation. It's the f of x, okay? So whatever curve is here, I don't know which one is, but I will tell you. Let's say, I don't know, something like, it has to be monotonic, but it could be a curve, any curve, a squiggly curve, it could be anything. It has this equation, okay? And I am asking you, well, it's this equation between 1 and 5 and 0 otherwise. So actually, your function is this, right? So it assumes 0 otherwise and assumes 1 and assumes a curve between 1 to 5. Okay? This is your function. This is your density function. Now, the question is, what's the probability of this being less than 4? Well, I know that to calculate probabilities, what do I have to do? I don't have a table. I just have a curve. I have to find the area under the curve, right? So here is it. Here's my 4. Can I ask this? What's the probability of x being equal to 4? Well, I can ask it, but what's the answer? It's 0, right? It's 0 because a continuous random variable will never be, you will never be certain. Remember, probability is a degree of certainty. You will never be certain if your value is 4.000000000 for infinity decimal points, right? But I can ask, what's the probability of x being less than 4? Well, the probability of x being less than 4 is the area under the curve between 1 and 4. Right? Is this area here will give me this probability. So the probability of x being less than 4 is actually the area under the curve. Okay? Fantastic. Okay. So now I will tell you a secret, and you will have to know the secret for the test. This f of x is an equation of a line. Okay? Oh, but I didn't know that. How can I know that? Well, do you remember that we saw what is a linear equation? Do you remember this? A linear equation is the equation of a line. That's why it's called linear, and it has this kind of formation. Y, or whatever you call y, it could be f of x. Okay, is equal to ax plus b. Look at this equation here. F of x is actually 1/8 of x plus or minus 1/8. If you separate the denominator into its parcels here, x over 8 minus 1/8, you have an equation of a line. Because the a here is 1/8, the b is minus 1/8, and this follows a linear equation. Okay? So this is very important because usually all years we have a question with the linear equation. So in the end, I drew this squiggly thing, this squiggly PDF, but it actually is a beautiful, beautiful line. Okay? So let's correct my graph. Now that you know, you will do it from the scratch, but let's correct my graph because this is a line. How can I position this line? Well, think about this. When x is 1, what is the value of my function? Well, put 1 there. This is 1/8 times 1 minus 1/8. This is 0. So I'm here, okay? What about x being equal to 5? What happens? Well, the value of my curve will be 1/8 times 5, right? Minus 1/8. Okay? This is 4/8, right? So this is a half. Let me put this 0 here, up here. So look at this. I have this point, and I have this point here, which is a half, right? Or 4/8. So if it's a linear equation, how can I draw? Well, just pass the line through these points, right? A line is passing through. It's the passage of a kind of a squiggle into 2 points, right? So this is the function. The function, it doesn't go. It is 0 actually before 1. So let's draw it right. Then when it's 1, it's a 0. It starts in 0. It grows as a line. And after 5, what happens after 5? Well, after 5, it's told to you that it's 0 again. So in the end of the day, here's my PDF. I start in 0. Then I start growing linearly as a line up until 5, and then I drop, and this PDF is 0 again. Okay? Cool? Good? All right, so let's find the area under the curve to find the probability of x being less than 4. So this is the area. It's the area under the curve, right? What area is this, guys? What shape is this? What shape is the blue shape? Sorry? A triangle. Do we know how to calculate the area of a triangle? Hopefully, yes. So probability of x being less than 4 is the area of this blue triangle. It's the width of the triangle times the height divided by 2. So what's the width of the triangle? It's 1 to 4, right? If you take a measuring tape and you put like 1 to 4, what's the width? 3, right? What's the height of the triangle? Do we know the height of the triangle? Oh God, we are lost. What can we do? Ideas. Does anyone have an idea? Yeah. I love you. Yes, exactly. It is that, right? It is that. So you have the equation of the line, don't you? If you want to find the value of the line here, right? When your x is 4, just substitute. Well, my line will be you can read f of x as being line. My curve will be equal to 1/8 of 4 times 4 minus 1/8. So in this point, when my x is 4, my curve will value, well, this is a half, right? Minus 1/8. 1/8 is 0.125. So this is 0. This is a half minus, this is 25. 5 this, right? Okay. Okay, I'm not good today to do by head. Let me go. Calc. It's a half minus 1/8. Oh, 0.0375. Oh, Jesus. Forgive me. 0.375. 0. .375. Okay, so this is the value. It's 0.375. Did I find my height? Yes, I did. It's here. It's 0.375, right? It's this measure here. Look, this is my height of the triangle. Okay? So 3 times the height is 0.375. And this is the probability. You don't need to work this out. Like, it's just leave it this way. Yeah.
I got lost about what you were doing with the height. Yeah.
So the question is, what's the probability of having 4, probability of my variable being less than 4, right? So to find that, I have the area under the curve. We know that this curve is a line. So just draw the line, find the values of the extreme points. And then this area here that's shaded is what you want, okay? How can we find that area? That area is the width times the height, this, right, over 2. This is like it's a geometry, right? The width times height over 2 is the area of the triangle. You have the width. Okay? It's 3, because you go from 1 to 3, right? 1 to 4. And then you have the height, because when your x is 4, you can find the value of the curve. And the value of the curve is this. That's the height. Okay? Yeah.
So are we expected to know what 1/8 times 4 minus 1/8
No,
is?
you could just leave it. You didn't even have to calculate. You could have just leave this here. You don't need to
Okay.
work it out. It's
Okay.
just
Okay, so how would you just leave it then?
oh, okay, yeah. You don't even need to calculate. So you could do this. If you were in a test, let's get rid of this. Just 1 second. So you could do, this is 3. This is 4/8 minus 3/8. This is 3/8, right? So you could just take this and put 3/8 here, and that is fine. Okay, you didn't need to work the decimals. Okay, it's fine. Yeah.
Could you just do 4 minus 1 divided by 8?
No. Yes, you can. It's 3/8, right? It's the same thing. Right? So this is very important, because sometimes, look at me. Sometimes you will see something like this: x minus ax minus b over 3, or over whatever. Okay? This is the same thing of having the separate terms divided by 3. Okay? It's the same thing. You divide first this one by 3, and then this one by 3. It's the same thing. This is it's important for you guys to know. Okay? Cool? So, but sometimes you will see a formula like f of x is 1/8 of x minus 2/3. This is also a linear equation. The only thing is that you're not dividing both parts to the same number, so you don't have like a common denominator, okay? You could have, but it's not here. Okay? I will talk, let me talk to you. I see that this is something that, let me talk to you after, because I'll do it in the board here, and I'll show you, okay? All right, so let's go, continue here, and let me just skip this, and, all right, so in the end of the day, we know that if you have a continuous random variable, your histograms that were like large, like this, starts to being narrow bins, lots of little bins here, okay? And if in the limit, because your continuous random variable can assume whatever value it is, these segments here, they tend to be points. And so in the end of the day, you'll have a curve. Okay? You'll have a curve. So this is our PDF now is a curve. And it has an equation. For example, in that here, it was a line. Okay? Here, it was a line. It could be a squiggle. It could be anything. But you just need to know the line in this course. Okay? The equation of a line. And the equation of a line is usually given by this. Okay? Cool? What else that we saw? That as in the discrete world, if I want to find the area, if I want to find a probability of x being something, like here, okay, I would have the area of the bin, okay? And it's the same thing, but now we use intervals, like from here to here, because we don't have a specific probability. So we're going to calculate the area under the curve. And again, the curve can be anything. For us in this course, it will be a line, because you're not required to know other f of x equations. But the way we calculate the probability, right, is the area under the curve. Okay? This is like a summary that we just had. Okay. Now, let's think about this. Let's think that I have a discrete random variable. Okay, so let's go back to the discrete. I have a histogram that I can list. Okay? But I know that it has a histogram, but imagine that this histogram is hidden from me. Okay? You're seeing it here, okay? But imagine that you didn't have it. There is a concept named good approximation. What is that? The good approximation concept is this: that sometimes a continuous random variable, so it's a curve, can be an approximation to the discrete random variable. Okay? Why is that? Well, because sometimes you don't have the histogram. This happens. You don't have the discrete histogram. You don't have it. You don't have the histogram. But you have a curve. You have the equation of a curve. Sometimes it happens. In research, it happens a lot. So you have an f of x. You have the equation of this squiggle here. Okay? But you don't have the histogram. So what you want to do, remember, you don't know that this has an histogram. You're not seeing the histogram. But you know that you can approximate the histogram by this curve. And you actually can. Look at this. Look, magic. Magic will happen. Look, everyone. 1, 2, 3. Yes, you can. Right? So the squiggle actually is so good. It fits the histogram very nicely. Okay? So again, you don't have the histogram, but you know the f of x. You know the f of x. And indeed, the f of x would be a good fit for the histogram. Okay? So if you have the f of x and you don't have the histogram, we can do an approximation to calculate the probabilities. Okay? And I'll give you an example. So let's say that you want to know the probability of x being between 1 and, so what's the probability of x? Remember, x is discrete. Your original random variable is discrete, between 1 and 3. Okay? And it could be equal. It could be equal because in discrete it can be equal. You would have to calculate this area, right? Look, the bin of 1, the bin of 2, and the bin of 3, right? This is what you would have to do if you had the histogram. But you don't have the histogram. What do you have? I have only the curve. I have only the curve. The histogram is on background, but it's just so that you can see that the fit is good. So what would you have to do? Well, the area, you would have to calculate the area under the curve. And the area under the curve would kind of approximate the area under the curve. So this would be, let's say that the x was the discrete, and now I have a y, which is the continuous. Okay? So this is the same thing as this, right? And you can drop the equals, because now you are in the continuous world. So you will have to do the area under the curve. And somebody can say this, oh, but look, this is not perfect. Why is not perfect? You're missing these little parts here, right? Can you see these little parts here that I'm not shading? I'm not shading these little parts. Why is this a good approximation? Well, because think about this. Here, for example, okay, let me just shade it a little bit more so that you can understand. So this, can you see that I have some shaded area that is more than the bin? It's here. It's outside of the bin. This compensates this one. Okay? So I'm losing a little part of the bin because the squiggle it's approximation. But in the end of the day, I have areas that compensate the loss. For example, this area here is compensating the loss. Okay? So it is a good approximation to calculate the area. If it's a good approximation to calculate the bin area through this curve. Okay? All right. So let's do an exercise to practice. How can we do that? All right, let's go. Suppose y is a good approximation for a discrete random variable x. Okay? All right, so I have a discrete x. So I'm in the discrete world. And I have a y that is a continuous. So here I would have a histogram. Here I would have a f of x. Right? A curve. All right. So say that x takes values 0, 3, 6, 9, 12, and 15. Okay? Do I have the histogram? No, I don't. And look what it asked for me. I want the probability of x being between 3 and 12. If I had the histogram, I just calculate the area between 3 and 12, right? But I don't have it. But I know that y is a good approximation. Okay? So let's do a mock, let's construct a mock histogram because I don't have it. But let's construct a mock histogram. So I would have a bin centered in 0, I would have another bin centered in 3, I would have a bin centered in 6, I would have this one centered in 9, this one in 12, and this one in 15. Okay? Is this the original histogram? No, this is a mock histogram. I don't have the histogram. I don't have the heights of these bins. I don't have anything. But I know that there's a curve, and you can draw it loosely. You can draw very loosely. But I know that there's a curve that approximate. I know that there's a curve that approximate this. Okay? You can draw it by hand, like passing through the center of the beans, okay? This is f of x. And I have f of x. Okay? It wasn't given to me here because we're not like doing the whole problem, but you have it. I have it. I have it. I have it. I have f of x, okay? All right, cool. So how can I calculate this probability of x being in between 3 and 12 by using y, by using the f of x? Well, I could say that it's the same thing as measuring the continuous random variable, okay? But in what interval? So let's find the interval. Look at this. In the discrete world, you want the probability of equal to 3, okay? You want the probability of equal to 3, right? So in the discrete, if you had the histogram, you would calculate the area of this bin, right? Because it's the bin related to 3. Then you would calculate the area of this bin. This bin is the of 6, of 9, and of 12. You would have these bins, right? Okay. Now let's find the area under the curve that corresponds to this. Well, take a look at the blue stroke here. Look. I would have to include the bin of 3 and I would have to include the bin of 12, right? Right? So, what is the interval that I have to take? So I want actually, the green one is if I have the histogram, but I don't. So in the end of the day, what I'm doing is I'm calculating the blue as an approximation. The approximation should contain the 3 bin, the 6 bin, the 9 bin, and the 12 bin. So what's the interval that I'm talking about in the continuous world? In the continuous world is the blue world. So this is the blue world. And this is the red world, the green world. The green. Well, the interval is not 3 to 12, is actually 1.5. Why? Because you have to include the bin of 3, right? You have to include this bin. In the curve, to include the bin, I have to take 1.5. If I want to include the bin of 12, I have to go up in my curve up until 13.5, right? Which is the middle of the interval. So this is what you need to do. The good approximation that gives you this probability for the discrete value is actually when you get the area of the curve 1.5 to 13.5. Okay? So let me paint this into another color, so just to get this distinct. This is the curve. Okay? The curve is this, and the light blue is the area under the curve. Oh. Okay. This is the curve. And I want the area under the curve that includes the 3 bin. Perfect. The 3 bin, the 6 bin, the 9 bin, and the 12 bin. So to include these bins that I don't have, but I know that the bin of 3 starts at 1.5, right? Do you remember this? And to include the bin of 12, I would have to go up until my curve. I will have to take the point of my curve here, that goes up to 13.5. Okay? And if you have the f of x, then you just calculate the area in the continuous variable. Okay? Now, here's a question for you. What if I asked you, actually, if I want to calculate this, look. Meaning that in the green world, I don't want to include the 12th bin, the bin corresponding to the 12. What would be the interval in the continuous world that I could do that? So I want to include the bin 3, right? So I have to start at 1.5. This is cool. And I'll go 6, and I'll go 9, and should I include 12? No, I don't want to find the probability of my discrete random variable being 12, meaning that I don't want to calculate the area of bin 12. Okay? So I would have to stop my continuous random variable here. Look, I would have to stop it here. Oh, sorry. I would have to stop it here, right? Why? Because I don't want to include. So this is the yellow. I don't want to include the 12th bin. So I'm going to take the value of my curve in my y. So my blue curve is y, and my red curve is x. Okay. So in my y, I will have to take the value of y up until 10.5. Right? 10.5, right? It's in the middle of the interval. You have like 1.5 here and 1.5 here. Yeah? Okay. Yeah. But did you get it? The area of the new part here, which is the yellow area, will include 3, will include bin 6, will include bin 9, and it won't include bin 12 because I don't want 12. I don't want an equal 12. I don't want that. So in the end of the day, when I'm looking at only y, I should go from 1.5 to include all these bins and stop at 10.5. Yeah.
12 is greater, so I can't use it.
Sorry?
The 12 is greater, so why couldn't you underline it?
12 is greater where here?
Yeah.
Actually, x is less than 12, right? You read this as x being less than 12 and greater or equal to 3. Okay? This is more common than you think. Like the having this kind of confusion. This the sign, the inequality sign, it points like it takes. Imagine as a triangle, right? It's taking the great and going to the small. So you're saying that x is in the point here. It's actually smaller than 12. 12 is bigger. 12 is bigger than x. Okay, so x here is smaller than 12. That's how you read it. So you don't want to include 12. You don't want to include 12. You don't want this bin to be included. So if you are in the continuous world, if you're looking at only at the squiggle, you would have to stop the squiggle here and take only the yellow area. Why? Because you don't want to include 12. Okay? This will be on the test. I already saw the test. This will be on the test. You will have to learn how to calculate the probability of a discrete random variable using a good approximator of a continuous random variable. What is the thing that you need to know? How to find the interval. And the way we do it is this. First, do a mock histogram to find the bins, the interval of the bins. Okay? Then pass a mock line, a mock squiggle of your continuous y. Okay? And think about what you want to include or exclude of your area. Okay? If you want to include 3, you should start earlier than 3. Okay? Because your squiggle is continuous. If you would take only on 3, look at this. If you take only in 3, you would be losing half of this area. Okay? So this is how you do it. Mock histogram, mock squiggle, find the interval. After you found the interval, then you can continue calculating whatever you need to calculate. Okay? Yeah.
Why would you have to do a mock if you just, couldn't you just look at the probability and just say, okay, so if it's 3,
Mm-hmm.
I automatically have to subtract 1.5 from the first one if it's equal or greater than,
Mm-hmm.
add 1.5 to the second one. Why do you have to do all that extra?
Because where do you get the 1.5 information?
Because that's what you said, is to get before that is 1.5.
Yeah, but
and after.
you know that this is 1.5 because I drew it. I drew. Yeah, right?
Yeah.
Because if you didn't have, like, if you don't draw, you won't know, like, that this here is in between 0 and 3. Like, I mean, you could see that, right? Like, as a illumination or something. It can happen. There are people that have this, that have this ease, but it's not my case. So I have to draw. Okay, draw the mock histogram so that you know, like, the intervals, and then you will see that it's 1.5. After you saw that it's 1.5, you can do that, like, the reason that you're doing.
Yeah, so
Okay.
I'm asking, because since it's a mock, essentially you can draw the intervals wherever you want.
Yeah, sure.
It doesn't matter.
Yeah.
But if you're using it in a numerical sense, is it always gonna be 1.5 in front and 1.5 on the other side?
No.
So then
It depends on what the discrete random variable takes on, right? So if your discrete random variable was 0, 2, 4, it would be 1. So look at this. This is a great question. Great question. And we will practice in the recap. We will do exercises and then you will see. If your discrete random variable took on 0, 2, 4, right? Whatever it is here, and you want to include 2 in your, you would have a y here, a continuous random variable. If you want to include, like, 2, you would have to start here, right? you would have to start your area calculation here. And this is actually 1.
So it's always
Right.
half.
It's always half. Exactly. It's always half. But it's half. It depends on this interval. Okay? So, I mean, you can do directly. I would suggest drawing so that you don't get it wrong. Okay? Don't get it wrong. Just it's a simple sketch that you can do like a side, and it will lead you to the right answer. Hopefully. Right? Okay. Cool. Yes.
Sorry, so if you were to do this on the exam, then your answer would be probability equals 1.5.
Yes, it would be, yeah, it would be the green parts here.
Yeah.
Like if this one would be this one will be that. But in the test, it might be that then he continues asking, like, okay, find that probability, and now that y is f of x, right, is equal to the, like a line, right? Then you should find the area of that, okay? So you would find the area under the curve, okay? So I'm doing just the interval here, but we will do complete exercises in a bit, okay? More questions? Good? Okay, so now we're going to go back a little bit to statistics. We did discrete random variables. We went to statistics. We learned how to calculate average, mean, expected value, and standard deviation, and variance. And now we're going to go back to that statistics, but now to continuous random variables. And it's crazy, okay? So if we don't take calculus, mean and variance and standard deviation of continuous random variables are like you need calculus to do it by hand, right? Because the mean, the expected value of a continuous random variable, is the integral of x of f of x times x, the probability times x. It's the integral of the curve, and we don't want to go there, right? Yeah.
Yeah, never mind.
Yeah, well, no, we're not going to see the integral, okay? So what we're going to do is we're going to learn how to read things that people already figured out, okay? We're not going to learn how to do the math. We're going to learn how to read the math, okay? So there is a special random variable called the standard normal random variable. It's the famous bell curve. It's this one, okay? So when you say normal, I have a normal random variable. It's a normal, right? It's this bell-shaped random variable, okay? But there's a family of bell-shaped curves. You can have a bell-shaped curve like this. Look, like this. This is maybe the standard. Then you have one like this. You could have one like this, right? This one can have this graph can be positioned at 3. This graph can be positioned at whatever, 100. So you can have whatever curve that is bell-shaped is in the family of the normal curves, okay? But there's one that is even more special, and it's called the standard normal. So it's kind of it's very normal, right? It's the standard normal, and it's the pattern is the standard, okay? This curve, the standard normal is this one I'm showing you, and its graph is positioned in 0, and you have a standard deviation of 1. Okay? So let's recap a little bit. I have a random variable. I'm telling you that I have a random variable, that when I draw the PDF, remember, the PDF of a continuous random variable is a curve, right? A squiggle. When I draw a PDF of a standard normal random variable, this means that the squiggle of the PDF is a bell-shaped curve. And if it's a standard normal, the squiggle is like the upper part of the squiggle is centered in 0, okay? And has a standard deviation of 1. Remember, standard deviation is how spread is your distribution, okay, or your histogram. In this case, our histogram is a squiggle. How spread is your squiggle, okay? So this is what we call the standard normal. There are other normals. Yes, there are other normals. For example, this one here is centered in 50 and might have a standard deviation of 20. It's more, can you see it's more spread? It's even more spread. It's more spread than this one here. This one has a center of 100 and can have a standard deviation of 2 because it's very narrow, right? Okay? All of this are in the bell curve family, but only this one is the standard. Okay. Cool? Cool. So, how do we call this variable? If you remember the beginning of our lectures in random variables, I said, oh, random variables can take on capital letters. X, Y, W, whatever you want, but not Z, right? That's the reason. Because Z, we kind of kept that exclusive to this curve, okay, to this random variables. Random variables that have this PDF, this squiggle, in their PDF, they're called the standard normal, okay? So that's why Z is exclusive to this random variable here. Okay. So, why is this important? Why is this important? Well, it is important because mathematicians kind of found a very neat way to calculate the area under the curve, or the probabilities of this standard normal, okay? So there are two reasons why we study standard normals. First of all, lots and lots and lots of things in nature follow the standard, the normal distribution, the bell shape. Okay, not the standard, but the bell shape. So, for example, if I sample everyone here, and I take a note of our heights, okay? And when I do the histogram, it will be a good approximation of that histogram would be a normal, a bell curve. Meaning that, look at this. There is more probability, there is a kind of less probability of someone being between 188 and 2 meters, 198 and 2 meters, right? Because look at the probability. Remember, this PDF is a curve, and the area under the curve gives the probability, right? What's the area under this curve here? It's very small. So, and this is what it is. It's very hard to find a person with 1.98 meters, right? Or near 2 meters. It's very rare, actually. And, well, these new generations are taller, but anyways, it's very rare. And it's very rare to have very small people, right? It's very rare to have a person with 100 to 101 or 102 centimeters, like around 100. It's very rare. The area under the curve is very rare, okay? But let's say, well, we have 2 men here, 2, 3. But let's say that we have this is the height of girls, of women. We're women now, right? Although I consider myself a young girl still. But this is the height of women, okay? The height of women will be, like, in average, like, it's more likely that most of girls, they are in between, like 160 and 175. It's the greater area. It's the greater area under the curve. It's more probable. It's more probable that when I random sample here a person, okay, I'm randomly pointing to a person. What's her height? So it's more likely that this height is in the greater part of the bell curve, okay? Because the area under the curve is bigger. What other measures we have? Well, height, weight is like that, right? It's very rare to have somebody that weighs a lot, and very rare to have somebody that's super skinny. In general, everybody has to lose 2 or 3 kilos, and we're in there, like in the mean, right? The mean is here. It should be 165, for example, something like that. Okay. So we're near this mean, this average, okay? Now, all of this weight means lots of variables are this way, so that's why it's important to study bell curves. But the bell curve that we are studying doesn't have a mean of 165. It has a mean of 0. It's centered in 0, okay? Remember, why do I'm saying that this is the mean, the expected value? Do you remember the definition of expected value? Expected value weights the probability, right? Remember. So if it's in the center, if this is the probability density, I'm weighting it, so the center is the mean, okay? All right, so it's super important. And then because mathematicians got a very good way of measuring the probabilities of the standard normal, we're going to study it. Okay? So that's why we're going to do it. Okay? How did mathematicians get to calculate probabilities in the standard normal? Where they come up with a table, thank God. They started integrating and calculating the area under the curve. F of x here is an exponential. It has an exponential kind of a shape. It doesn't matter. Doesn't matter the way they did it. Doesn't matter. In the end of the day, the way we are going to do it is using the table that they came up with. Okay? And this is called the z-score table. And we're going to learn how to use it. We're going to learn how to read it. We're not going to calculate it, thank God, okay? So, what is this table about? Well, this table, if you can see, there's a row, and there are rows and columns, right? So rows are here, 0, 1, 0, 0.1, 0.2 up until 1. Actually, you can go further. It goes up until 8, 9. And here in the right, you have 0.001, 0.001, 002, 003, and so on. Okay? When you see this thing in the wild, you will usually see an indication of what the table means. Look at this indication here. It's indicating that the number you're finding in the table is the area under the curve. Okay? So can you see, I don't know if you can see, this is a little z here. So let me tell you this. We are talking about a standard normal. It's a capital Z. Okay? And you have a little z here, meaning that your variable can assume this value. Okay? The standard normal can assume from very, very small numbers, negative numbers, up until large numbers, okay? You cannot list them. But let's say that you want to do this range, meaning that what's the probability of your variable, z, being less than little z, okay? So it's this area under the curve. It's the green area. Do you agree? Okay, how can I find this probability? Don't mind doing the integral and calculating whatever the area is of this squiggle. The equation is ridiculously difficult. You will look in the table. For example, let me show you this. What's the probability of z being less than, let me see, 0.72. Okay, remember, we are in the standard normal. This is 0. The center, the mean is 0. What's the probability of my variable being less than 0.72? It's this green area. Well, I look into the row. It's my first digit, 0.7. And then I look at the column. The column brings my second digit. So it's 0.7 and then 0.02. Okay? Because this is 0.7 plus 0.02, right? Do you agree? So then I will cross them and I will find the figure that I want. This is the probability. So this, the probability of my z being less than 0.72 is actually equal to 0.7642, which is 76.42%. Thank God we're not calculating anything. It's just kind of going to a table and finding out the probability. Okay? Another example. What's the probability of z being less than 0.73? What should I do? Oh, I got the same digit. 0.7. It's the first digit, right? What's the second digit? 0.03, right? Because 0.7 plus 0.03 is 0.73. You will find the figure in like crossing row and column. Let's do another one because it's too similar to the other. What's the probability of being less or equal to 0.39? Can someone find it for me? No? Yeah. 0.65, yes, 0.6517. Oh my God! What we did here is I went to the first digit, which is 0.3, right? See, this is little z. Little z here will value in the first digit it will be 0.3, and in the last digit it will be 0.09. So I come here, 0.09, and I cross the column with the row, and I find the figure. This is the probability. Cool? Nice? All right. Now, there's a problem with this table, and then I'll leave it here, but we will see there's a problem. Unfortunately, nothing is as good as we wish. So if you take a look at this table, it starts at 0. So it means that you can calculate this probability. You start with this area here, and then you start growing the z, right? So you start with the area, just the left area, when little z is 0, and you start growing the z, okay? But what if I want this area here? I don't have it a negative number in the table. So what's the probability of z being less than minus 0.2? I don't have that. Sorry? No, you can.
No,
I didn't hear it. It's okay. So minus 0.2, I don't have how to assess this in the table, right? Because the table starts at 0. It gives me, so the first area here okay, is the area between 0 and the tail here, the left tail, which it has to be a half. Do you agree? Do you agree that the probability of being less than 0 is a half and more than 0 is a half? Right? Because you have a centered distribution, okay? And half of the distribution is on the left, half of the distribution is on the right. Half of your people will have height less than something, half of the people will have, in, like, if you sample a lot, will have height bigger than 165. In this case is 0 because we're talking about the standard normal, okay? So the probability, the area under the curve of being less than 0 is a half. It's this area, it's half of the area. But I don't have this case here. I don't have negative numbers. And so we will learn how to tweak the table to calculate that. Okay, next lecture. All right, questions? Good, lots of things. This is recorded, so if you want to go back, take a look. Okay.